Welcome back. I know I went over the simulation within the previous video, but we'll actually do some examples with the different spice directives right now together. I'll just be remaking this circuit, but live for you guys. So to start off, let's say we need a voltage source to start off, right? So we search up a voltage source, press OK, and we place it wherever we want. To get rid of it, you just right click on your mouse and it gets rid of whatever component that you might have. And we're trying to simulate current division, so let's have a bunch of resistors in parallel. So we'll have three resistors to be exact. And we can actually connect these up using F3 or click on this for wire. And then just connect them up. Try to be a little bit neat. I usually am not neat when I'm designing circuits, but again, just connect up all these resistors in parallel. And then how you would change the value of each resistor is by right clicking on the resistor, and over here you can change the value. So let's say we want 10 ohms, we will say just 10, right? Let's say we want 1,000 ohms, so 1 kilo ohm. We can actually just put in 1k and it registers this as 1,000 ohms. But for now, let's just stay at 10 ohms, and you can select specific resistors as well if you're trying to be very precise with the real life components that you might have. So, but we're not going to do this. We're just going to have a normal resistor with, well, ideal resistor with 10 ohms of resistance. Now, if we made all of the resistors 10 ohms, the current across them would be basically the same. So I1, I2, and I3 would just be the same. So we don't really want to do that. So let's make this one 20, and then let's make this one 30 ohms. And we'll see how this works. Always don't ever forget to include ground. I always do that. I always forget. But now that we have ground, we're almost set, but we have to set up the voltage source as well. So let's say the voltage source is inputting 10 volts into our circuit. Again, ideal voltage source. So press OK, everything's good. Now, the way it is right now, we can't really simulate anything because we don't have a spice directive. So either what you can do is click run, or go up here and click simulate then run, but just click run, and then you can use the spice directive directly from here. So we have transient, AC, DC sweep, etc, etc. Or you can use this spice directive icon right here, and what we want to simulate right now is a dot op. So we'll just do a dot op spice directive and drag it wherever we want within the schematic. Now that we actually have a spice directive, we can actually simulate this and get some results. So let's simulate this. And with the op spice directive, you're usually going to pop up with this tab right here. Depending on the amount of nodes that you have, the amount of components in here might differ, or the values, not components. I'll actually label all the nodes real quick, so we actually understand how this is operating. So we actually technically only have two nodes because everything's in parallel. We have node 1 and then the ground node. So I'll just do, let's just call it node ground. Node ground down here. And we're gonna be checking basically the voltage at node 1. So I'll actually run it and show you guys exactly what's happening. So we see voltage at node 1 is 10 volts. So again, parallel resistors voltage is going to be the same across all of them. And then we have different currents. So we have currents for every single individual resistor and the voltage source as well. Now you might see negatives or positives over here, depending on the orientation that you put the resistors. So if I were to, like, let's say reverse these resistors, actually let me do that real quick. I'll grab this and then I'll rotate it all the way, grab this, rotate it, and then grab this and then rotate it. And then let's run this now. So as you can see, all the currents became negative. So the orientation of your resistor does matter. And if you want accurate results, make sure that you have the orientation in a correct way. It's much more difficult to do that within the schematics rather than a netlist, because you don't really see which side is going to be which side. But regardless, let's run this again. So again, voltage is the same, and since our resistor values are different, the current actually gets distributed differently through current division. So I'm pretty sure you guys know what current division is, but I'll do a quick refresher for you guys, just to make sure. So let me open up. I'll just open up a new page within one of my classes, and we'll go through what current division essentially is. But you guys, if you're taking 211, you should be learning this very soon. So with parallel resistors, we know that with series resistors you can just add them up, but with parallel resistors you have to follow a specific rule to adding up a resistor. So let's say we want R total of this whole circuit, right? So we go to draw. Let's go to draw first. Let's say we want R total, and we have three resistors in parallel. So what you would do is to get R tote, I'll just call it tote. R tote is basically going to be equal to R, I, etc., etc., etc. Any resistor plus, let me redo this so it makes more sense. R1 plus R at I, whatever resistor might be, and you keep on going. So with this, you can find the total resistance of the circuit. In our case, I'll actually have to calculate this since I'm doing this on the fly. So 1 over 110 plus 1 over 20 plus 1 over 30, we get 0.183. So make sure that you divide this, so do 1 over 0.183, because to get the R total you actually have to do the inverse. So what we'll do is just 1 divided by the answer, and the total amount of resistance within this circuit schematic is actually 5.45 ohms. So now that we know this, we can actually find the input current that is accumulating over here. So all you would have to do is remember Ohm's law, V equals IR. So to find the current, you would just do V over R. So we have 10 volts over the input resistance, and our actually, I'll run this too. And our current should be 1.833, which it is. So we can confirm this through LTspice that our method of getting the current is correct. Now, current division, on the other hand, is essentially somewhat similar to voltage division, but it's a tad bit different. So I'll actually go through that real quick with you guys. Let me open up notes. Okay, so we went over how to get the total resistance when you have parallel resistors. So let's say, like our circuit, we have a voltage source. Then we have, I don't know how to draw, sorry about this. Then we have one resistor, two resistor. I'm drawing with a mouse, I'm sorry. Three resistors. Now, this right here is going to be I1, this is going to be I2, and this is going to be I3. Now let's say we want to find I2. I'll actually label the resistors first. So 10 ohms, 20 ohms, and then 30 ohms. So now let's say we want to find I2, right? So to find the current at I2, so I2 essentially is just going to be equal to 1 over R2, which in our case is 20 ohms, over 1 over R1, which is 10 ohms, plus 1 over R2, which is 20 ohms, and then 1 over R3, which is 30 ohms. Now this continues, so like let's say we had even more resistors, you would just continue this on, and then you have to multiply our initial I. So let's just call it IN, right? So we multiply IN by this, and we should get our current at the resistor that we're trying to focus on. So I'll calculate this out real quick, I guess. So 1 over 20 over 1 over 10 plus 1 over 20 plus 1 over 30. I actually did this already. You end up with like 0.27. Multiply that by 1.833. Etc., etc., and then you're going to end up with a zero point 0.5 for I2. Now let's confirm if that is actually the case. So like let's run it again. I2 should be 0.5. So we can confirm that the way that we are calculating these does hold up, because LTspice clearly shows the results are very similar. and vice versa. We can confirm that LTspice is correct based on what we calculated. Now that we have done a basic .op directive, let's actually move on to a DC sweep. I think that'll be pretty dope. Let me cross this out, and then I'll just make a whole new schematic. I'll try to follow the slides that we have, or rather the examples that I have put on the slides. So people that are watching the video and people that are just looking over the slides, they're going off of the same thing basically. Let me let me open up the slides. I actually accidentally closed them real quick, and we'll go over the DC sweep real quick. So, oh, okay, perfect. So, in regards to the DC sweep, I actually did a series circuit within my slide. So, let's add in a component. Let's add in a voltage supply, and then let's add in multiple resistors. Let's just have three, like we do in the slides. Uh, I'm not gonna label the nodes. Y'all know. Actually, you know what? I'll label the nodes. I need to separate these out a little bit then. And to zoom out, I'll just zoom out with my scroll wheel. Uh, get this over here, and then now we just need to connect it up using the wire icon. So connect this, connect it all the way back, and then always make sure to add a ground. Okay. Now that we have connected everything, all we would have to do is, well, first of all, label everything. So let's just label all of them 10 ohms. This one as well, and then we'll keep the same voltage. Uh, we're doing a DC sweep, so the voltage that we put in over here is going to be the maximum voltage that we want. So let's just say 10, and we'll just sweep from 0 to 10. And then now that we have set everything up, all you would have to do is type in .dc. And then we want to do a DC sweep, so essentially all you would have to do is type in the source. So our source's name is V1, but actually let's change this to, let's go to advanced. Oh, not this. Cancel. Okay, guess I can't change the name. We'll just keep it at V1 then. DC, and then let's just say V1, and then we want to start from 0 and go all the way up to 10. Let's do 1 volt step size. So we have this here, and then we can right click this actually to see exactly what's going on. The sweep is going to be linear, of course, and then we can actually run this. Now with the DC sweep, you have multiple points that you're measuring, so 1 volt, 2 volt, 3 volt, all the way up to 10 volts. So you would either right click and add a trace, so add a trace at like any of the nodes. But what's useful when you're making a schematic is you can actually just click on whatever node you want. So let's say we want node 1. We got node 1, node 2, and then node 3. Now you can see it's a linear rise because it is just a voltage divider circuit with multiple resistors, and we're just incrementing the voltage from 0 to 10 in like 1 volt increments, and you can see how the circuit behaves at each individual voltage level. So this is essentially how you would test these, or test a circuit at different voltage levels using LTspice. So forgot to label the nodes. Do that real quick, even though I'm probably gonna end up deleting this, but always important to know where your nodes are. So node 3, and then we have our ground node, so we'll just say node ground. Yep. And then that's pretty much how you would set up a DC sweep within LTspice. Next, we'll actually do we'll do transient time before we do AC analysis, because AC analysis directly ties into an example we're going to do with a low pass filter later. So let's start off with just transient analysis. So for transient analysis, we're going to need a sinusoidal input. So we're still going to want to get the voltage source. So we plop in our voltage source, and let's make sure that we're using the same circuit. Okay, I guess Didn't have to delete the previous circuit because we're using the same circuit again. I won't label the nodes this time, but uh, you guys know where the nodes are. Just connect everything up again using a wire, and then connect it up, and then did a little bit too much, snip that off, add a ground, and then just connect it up, and then we'll label all these 10 again. Okay, and the voltage source, since it is going to be sinusoidal, what you can do is go to advanced. Now, as you can see, there's multiple different things you can do. You can do like a pulse wave, so like a square wave, or you can do a sine wave, exponential, etc., etc. For now, we're going to work with a sine wave, so we say sine. The DC offset is just going to be 0. Let's say our amplitude is 10 volts. Hmm. Let's just say 10 volts, and let's say our frequency is 2 kilohertz. Again, just random. So we say, okay, everything's set up, and then we actually have to set up a transient directive. So what we can do is just type in tran, and we can just say stop when you get to 3 milliseconds, or we can actually give it a step size as well. So let's say there, and let's just simulate this, right? And then again, you would do the same thing. Click on run to simulate. Oh, I think I messed up. Wait, before I do anything, let me close this out. Then let's fix this. Okay, there. It was bothering me. Okay, so again, sinusoidal. This is gonna be voltage division. At these different nodes, we'll see this once I actually select each node. So as you can see, I selected the nodes, and we can see that through voltage division, at each of the nodes, the voltage is decreasing. So since I went over current division, I'll actually go over voltage division again for you guys. Now with voltage division, it is similar to current division, but it is also a tad bit different. I'll actually open up notes again and do some horrendous drawing. Uh, okay. Okay, that's as good as my resistors. That looks like I induct. Yeah, whatever. Okay, we have our circuit. Let's label them. So R1, R2, and then R3, and this is gonna be our VN. Now, with current division, what you were doing is you were selecting the resistor that you wanted to find the current for. So like I2, we want to find the current at this resistor. So what you would do is 1 over R2 over the rest of like basically all of the other resistors, basically REQ, so 1 over REQ, and you would multiply with the current that is coming in. It is similar in the sense that you have to multiply it, but instead in this case it's going to be with the voltage. So let's say we want to find the voltage over here, so V2, right? So let's say we want to find V2, and to find V2, what you would do is basically take all the resistors after V2, so R2 and R3. So you would do R2 plus R3 over the R equivalent. R equivalent is just going to be all the resistors added together. So R1 plus R2 plus R3. And you want to multiply this by the V in. Our V in was 10 volts. So we can actually confirm this. So we all of our resistors were 10 ohms. So let's say in regards to this, we're trying to find V2, so it's going to be 20 over 30, because 10 plus 10, 20, then 30 down here, and then you want to multiply it by the V in. So let's say the V in, well, our V in was 10, so let's say the peak was 10, so let's say we want to multiply by 10. So the voltage at node 2 should be 6.6. So if we go back, so voltage at node 2 is blue. So at the peaks, let's check. It's basically around 6.6. You can click on the node variable up here to actually drag around to see where like where you're exactly looking. So let's get to the peak over here. Yeah, it's like basically 6.6 volts. So again, voltage division is confirmed within LTspice, and our calculations in turn are confirmed through LTspice. So again, voltage division very easy. The transient operation or the transient directive using the LTspice not netlist schematic over here, we pretty much understand everything in regards to that. So knowing this, we can actually move on to AC analysis. So for the AC analysis, I'll actually set up the same circuit we're going to use for the example, the low pass filter example I'm going to do. So I don't need to look over there. I'll just set it up real quick. So we'll get another voltage source. We're going to need one resistor for this low pass filter. And then we're going to need one capacitor for this low pass filter. Now we're just going to connect everything up. Connect that, then connect that to this, connect up the circuit, and then we want a ground, of course, and then connect up the ground as well. Now, since we are going to be doing a, well, actually, let me label these up. So I'll label this 1 kilo ohms because I'll go over this later on, but for now, just know that it's 1 kilo ohms, and this is going to be 31 0.8 nanofarads, so nanofarads, and you can just label it just like that and it'll actually register it. And now, since we are doing AC analysis, the voltage has to be set using this right here, AC analysis. So we want to have, let's say, an amplitude of 1, and then phase is going to be 0. So we set our voltage up real nicely right now, and then now that everything is labeled and set up correctly, we can actually add the spice directive. So what the how you do AC analysis essentially is you do AC, and then you do dec. So you don't have to capitalize it, you can just keep it lowercase. But what dec is basically saying is that we want to go from a certain frequency to another certain frequency at a certain frequency step size. So let's say we want a step size at 1000 per decade, and then we want to start from 0 all the way up to 10 kilohertz. That works, right? So we have it right here, and then we can simulate this. Oh, wait, I think it wants us to select one over here. Okay, then we can simulate this because we have everything set up. So again, this is going to be simulated right here. And then we want to find the V out. V out is going to be right here. So again, this, as you can see, the dB scale is basically a bode plot. The dB scale does follow the trend that a low pass filter would, and we can actually confirm this is a low pass filter. No, we'll do this once we're actually doing the example. But again, as you can see, you would use AC analysis, especially when you're working with filters or any circuit that has to do with the frequency domain, where different frequencies would affect the circuit in different ways, etc., etc. So now that we know about these different spice directives, we can actually get into an example using one of these spice directives, which is going to be AC analysis, and we'll do a low pass filter design, basically the same exact design that we did in the MATLAB workshop, but in LTspice, so you guys can see the difference within MATLAB and LTspice in regards to the same circuit. But with this, I'll conclude this video, but in the next video, I'll pick up again, but with the low pass filter example. So see you guys very soon.